Okay, so welcome everybody to today's special ITC seminar. We are very fortunate today to have our doctoral professor Andreas Burkert visiting us this week, known to us as Andy. Andy got his PhD during the Bush administration in Munich. I will tell you which Bush administration.
Where is?
He spent a few years after that in the United States before returning to Germany, eventually to Munich. He was a professor for a number of years. Andy has a long list of honors, including being a member of the European Academy of Sciences and Arts, a Max Planck Fellow, and he even has a minor planet named after him, not to mention the density profile. So in addition to all these honors, of course, Andy is a great person to have around and to talk to, so I encourage you all to do so if you have a chance. He's here for the rest of the week. But in the meantime, let's hear Andy talk to us.
Well, thank you very much. John. This is really good. I mean, what is this about? Well, actually, I looked into here. Has anyone looked into this here? There's kind of all kinds of interesting stuff inside. You need to look inside. We didn't dare to take some keys, so we probably haven't checked it out. It's amazing. So, but the whole history of this place is hidden in here. Anyway, skeletons we didn't find, but we didn't look on that side, so maybe it's on this. Black holes, well, it becomes yours, you see. Well, yeah. Well, the black hole wouldn't sit inside. It will all the way penetrate towards the center of the Earth and then begin to oscillate. Yeah, so, yeah, you even know. So, but that's not what I want to talk about. I would like to talk today about something which is a big puzzle for me and my fellow scientists involved in this, and this basically involves the group of Reinhard Genzel and at the MPE, where this whole project started, and I'm more the theorist, getting the fun part, interpreting, but I failed this part, and so that's why I'm here and asking you to help me. And I have some spies. She will tell my observing scientists that I didn't come up with it myself. Someone else, Ari, for example, had the idea, but we still have to talk. Okay. So, what is it about? Well, there is something which everybody knows. If you take a spiral galaxy, the most interesting feature of spiral galaxies, which is a kind of a trademark of spiral galaxies, are the rotation curves, and especially the fact that rotation curves are flat. And this has been figured out by Vera Rubin a long time ago, and it's basically the result of the following process. Spiral galaxies are exponential in surface density, which we call a Freeman disk, and if you have an exponential surface density distribution, then you find something like that. You have a rising inner part. You get a peak roughly where you have the half mass of your disk, and then you see the rotation curve is again decreasing simply because you run out of gas and most of the and mass, and most of the mass is within the radius, and you get into this Keplerian decline. But exactly where the disk is going down again in rotation, you have an additional component which we call the dark halo, which cranks up, and precisely when the disk is not becoming important anymore, dark halo becomes important to lead to this kind of flat profile. And it's still, I think, kind of a mystery for me that there's this kind of strong interaction between both components, such that if you look at the rotation curve alone, you wouldn't actually easily figure out where the transition happens. You know, it could well be that the disk is doing this and the dark halo comes up at the other parts. Then you would see a rotation curve which has a characteristic feature, a decline and a rise, and that's never seen. As if the universe is nasty. Right? It never easily tells us its secrets, and that's the same here. You have to figure it out somehow, but there's this kind of interaction between halo and disk that the rotation curves seem to be flat. And this has to be a paradigm. Everybody now believes in it. And if you find something that is not flat, I figured it becomes tough to explain it. Nobody believes it. Yeah? For me, this is actually the mystery, because you don't know what dark halo is. But for people, it's so well established that if you say, no, I find rotation curves that decline, people don't like it. Yeah? It's like the solar system. If you find a planetary system that's completely different to the solar system, people say, wow, well, I know how planetary systems have to look like. And so they don't like this idea. But that's exactly what I want to talk about today, declining rotation curves.
Which has another important implication, because some people explain this with modified gravity.
Exactly. We'll talk about this too. I don't discuss it, but it has implications for the nature of dark matter, maybe. Well, there's of course something else. You can try to, if this is flat, then there's a characteristic rotation velocity, and then you can see how this rotation velocity correlates with other things. And the most important correlation is the Tully-Fisher relation. The velocity correlates with the stellar mass, and it's just simply the fact that the dark halo and the stellar mass are correlating. And if you have a dark halo, then of course there's a correlation with the depth of potential well, and so these are things that seem to be very well established in cosmology. Okay, so this is what we all know about, and this is a redshift 0 universe. And when you now go to higher redshifts, the universe is different. And so the question arises, is there a change in the rotation characteristics of galactic disks or star-forming galaxies when we go to high redshift? So this is a typical redshift 2 star-forming, fast-rotating galaxy. Redshift 2 is especially interesting because that's 3 gigayears after the Big Bang, when you have the peak in star formation in the universe, where most of the stars are forming, where the chemistry or the nucleosynthesis is at its maximum, where you establish galaxy morphologies, establish the supermassive black holes, and all things break loose. And so that's the most fascinating part of the universe. And this is typical star-forming disks at high redshift. And one can now ask, okay, if we look at the rotation properties, how is the rotation curve of these galaxies? And that has been done in a recent paper published in Nature by Reinhard Genzel and us, and the result looks something like that. This is now the normalized rotation velocity of a couple of these high redshift galaxies, normalized to the maximum rotation, and the radius is normalized to that radius where you reach the maximum rotation, so that the scales has been taken out and you can all overlap. And what you can see is at first heretic and amazing. And that's why it is good for nature. And nature is not good for, where if you find something heretic, you publish it in Nature, not necessarily because it's better scientifically, it's just simply you come up with something else, and there's a lot of excitement as usual. So what you see is the inner parts, you might get again a rising part. This is depending on whether you have a bulge or not. Who cares about that? We're not interested in the inner parts. You have this maximum, okay, you have to have it, but then you see a decline. The rotation is going down, and it's going down not by a factor of 5%. It can go down by more than a factor of 2. Yep.
What is known about the velocity dispersion? Because they may become dispersion.
You are so clever. You could give probably the talk yourself. You get close to what it is. Yeah? But we'll have to see. I tell you more. Okay, so this is at first a couple of galaxies, and you now can put it together in kind of a universal rotation curve. We'd make a stack out of that. We actually have more galaxies than these kind of test cases here, or the examples, and then the whole thing looks like that. So this is the rotation velocity as function of radius as we see in this kind of stack sample. And compare this to the redshift 0 disk. What you would expect is something like that. If you take the Milky Way, it is flat, M31 is flat, and you see very clearly these high redshift galaxies do not behave as they should behave, if you think you know how the universe should behave. But I tell you, we never think about how the universe should behave, because it doesn't care about what you think. You should actually figure out how the universe behaves. It's always different than what you think anyway. Otherwise, it would be boring and we wouldn't work in this field anyway. So you see there's a substantial change. Now, there is something which is important. This is the Freeman disk solution. This is the solution if you have a pure exponential disk. Now, these disks are indeed exponential. So this is what you get just by looking at the baryons. And you see there is a problem that we are lying below this kind of curve. In addition, there is no signature of dark matter. I told you it could well be that the baryonic part is in an inner region, the dark matter is in the outer region. Then I would expect the rotation curve to go down and then crank up again. But there's no increase anymore. No signature that a dark halo adds in the outer parts, which would lead to it going up again and becoming flat or whatever. Absolutely no idea about dark matter in this kind of signature of rotation curve. And as I said, this is what you just would expect by looking at the disks you see. But the rotation decreases faster than that. Not only do you miss dark matter, if you lie above this curve, what is above is signature of dark matter. You lie below this curve. So it's almost like you have a negative dark matter mass, which, you know what I mean, not a gravity, but minus gravity, which is actually cranking these rotation curves down to something which is even decreasing faster than Keplerian decline. So this is the mystery. An explanation of that is what we have to find. And of course, you can blame it to the observers. And it's good to blame it to some extent because you don't want to waste any time on something that is an observational fluke. But the observers are very, very careful. And Reinhard and his group have done a very careful analysis of this kind of behavior. Do I have it somewhere? I thought I had it. Yeah, here. These are the rotation curves we see. So this is red is red shifted, blue is blue shifted. And you can see very well, we have this two-dimensional rotational pattern. You get this very characteristic spider-like profiles, which are characteristic for fast-rotating, quiescent disks without much perturbation. And it's very well possible to derive rotation curves from that, from standard techniques. You see there's not much of an irregularity. There are no companions. We don't see any warping or so on. All of these ideas you can come up with, which might mess up your rotational features, are not visible in these kind of objects. So as far as we know, if you can measure rotation curves with low redshifts, using the same technique should also work for the high redshift universe. And so it's not easy to come up with any observational problem that might lead to this kind of result. Okay, so I now want to assume that this is true, take it for granted and interpret it. And of course, there has been a lot of public response to this kind of paper because people said, wow, this is the end of dark matter. Forget about this. Dark matter has to be ruled out. We always knew this. And the Mond people liked it because dark matter was ruled out, but they didn't like it because rotation didn't become flat anymore. But they already had some revisions of Mond in mind. They always come up with a second parameter. And so lots of things. But I think I would like to do physics. And we'll try to explain it with physics, which I think I know. And if that really fails, then maybe dark matter is out or whatever. As I said, the universe decides what is right. So how do you do it as a theorist? How do you solve this problem? Well, here is the low redshift universe. Here's the high redshift universe. You try to find deviations or differences between these galaxies. And any difference you see can be a reason for this difference in rotation curves. Okay, so we'll try to do this. And at first you can say, well, this is obvious. This does not really look like this. Obvious difference. But if you go into more details, the differences actually are tiny. It's not such a big difference. Of course, you have less resolution here, but you still resolve the rotation pattern. There's no question about that. And then when you go into more characteristic properties, they are all the same. Both low and high redshift galaxies have stellar masses between 10 to the 10 and a few 10 to the 11 solar mass. The rotational velocities are not different. They are between 100 and 300 kilometers a second, and the disk scale length is between 2 and 8 kiloparsec. That's what we know very well from present-day universe, and it's the same there. And in fact, this is already a problem. That the scale length of these disks is the same is not what you would expect in the high redshift universe. The reason is the density at redshift 2 was higher, was a factor 8 to 10 higher. So everything should be a factor 2 or so smaller. So I would expect these disks to be a factor 2 at least smaller than these disks, but they are not. For the same rotation, they have roughly the same size. And that is already, in some sense, a hint of what's happening, and you will see later why it is a hint. Well, the rotation curve I already showed you. You can look at the Tully-Fisher relations, how the rotation velocity behaves with stellar mass, and this is kind of, if you put different galaxies, different redshifts together, this is where the Milky Way lies. Here's another sample, this is the higher redshift galaxies, they are lower redshift galaxies. It looks the same. There's not a big difference. There's not a completely different scaling relation. It all fulfills standard cosmology as we would expect to see it, independent of redshift. So that doesn't make a difference either. Then you can say, okay, maybe it's rotation, so it's connected to angular momentum issues. Yeah. And we know this very well. Usually how you phrase that in the lambda paradigm, where you say the angular momentum of a disk is just given by time, the radius of disk times its rotation, the specific momentum, and to normalize it to r times v, where r is the radius of the real radius of your dark halo, and v is the real velocity. It's basically square of gm over r of your dark halo. And this gives this characteristic lambda parameter of galaxies. And if you look at cold dark matter simulation and measure how much specific angular momentum you gain, when you bring all this cold dark matter together, you know very well that the lambda you get is of order 0.035. That means this is 1 over the collapse factor, which means you roughly have to collapse a factor 30 or so in order to get into centrifugal equilibrium, which the dark matter can't do because it's dissipationless, but which the gas can do. And we measured that, or the lambda parameter now for our high redshift disks. And here's the distribution. This is what you would get if you take adiabatic contraction of the dark halo into account. It doesn't work that well, so dark halo is probably not contract adiabatically. Whatever, the mean lambda parameters of your disk, of our disk, which we find at high redshift, is exactly what you would predict for the halos, what cold dark matter would predict. And so we think that the disk just remember the specific angular momentum of infall. And we also show that this lambda parameter is independent of redshift. We see it in the present disks too. They all fit the same result. So the specific angular momentum of these high redshift disks normalized to the dark halo is exactly cosmology and in a good agreement with low redshift. So there's no difference either. So high redshift galaxies are in some sense similar to this. And if this is true, and as lambda depends on real properties of a dark component, it's an indirect evidence that dark matter must exist around them. Otherwise, this would all not be working, and you could get any lambda parameter you can think of. So maybe these high redshift disks have dark halos, and these dark halos somehow hide and are not seen in the rotation or gravity part of these galaxies. Okay, there are also differences. And one of the most characteristic differences is the star formation rate and the gas fraction. Low redshift galaxies have slow star formation rates and small gas fractions of order 10% and less. Star formation rates of a few solar masses per year. The depletion timescale, which is the gas mass divided by the star formation rate, is universal at 10 to 9 years. High redshift galaxies have roughly the same depletion time, which for me is a big mystery because they could burn on a different rate, but they somehow don't do it. But the star formation rates are much higher, factor 10 to 30 higher, and the gas masses are correspondingly higher. So you can say maybe there's different physics in this kind of burning, which messes up the rotation curve or whatever. But it turns out the physics is actually the same. And that is what has been worked out in recent years. It's called this bathtub model I was talking about at the Black Hole Initiative, which was a challenge because these people just know about black holes. And I realized, going through my talk, they have no idea what I'm talking about. If you talk about a molecular gas component, this is so much lower density compared to black hole that for them it's zero density because. So I think I managed to get to the very end, and so somehow survived. I got a good lunch, so that's in the work. So they're nice. Anyway, so the bathtub model assumes that if you have a star-forming galaxy, it can only form stars because it accretes material from the intergalactic medium. Otherwise, it would burn out quickly because the depletion or the star formation timescale is 10 to the 9 years, which is short compared to the age of a galaxy. And then you can write down this very simple equation. The gas mass in a galaxy changes because it accretes minus the star formation rate. And you, of course, have a certain factor here. 50% of what you put into stars is thrown out again in stellar evolution. And you also lose some gas in the wind. The wind loading factor tells us how much mass you lose per time scale in the wind compared to how much mass you burn into stars. So usually the wind is correlated to the star formation, and this factor is order 1. So you see this is 0.5. 1 plus 1 gives you 2, minus 0.5 gives a factor 1.5 is of order 1. So you see that the change of the gas mass in a galaxy is accretion rate minus 1.5 star formation rate. What else can it be? And you can easily demonstrate that this very quickly, over 10 to the 9 years, approaches an equilibrium where the gas mass is not changing anymore, and what you accrete is just simply turning into stars. The star formation rate, again, you can write as the gas mass divided by this 10 to the 9 years of star formation time scale. So the gas mass is the star formation rate times this universal star formation time scale. You put it all together, you find the star formation rate is the accretion rate, and the gas mass is the accretion rate times 10 to the 9 years. And that immediately explains the high and low redshift galaxies, because Milky-Way type galaxies nowadays accrete 3 solar masses per year or 4 or 5 solar masses per year. That's why the star formation rate is that low. High redshift galaxies have accretion rates of 100 solar masses per year. That's why the star formation rate is high. There's not a different physics, it's just simply that there's more accretion. The gas mass is proportional to the accretion rate. The Milky Way accretes with 3 solar masses per year, so the gas mass is a few 10 to the 9 solar masses, because this is 10 to the 9 years. The high redshift universe, the accretion rate is 100, and therefore, naturally, the gas mass must be higher. It's all the same story, just simply different accretion, but the physics is the same, and that cannot explain these rotation curves either. Well, let's look into more details at some of these galaxies. This is a galaxy sample again, as we had it before. But now we do not show the line of sight velocity profile, which gives you the rotation. Now we show basically the emission of light in star formation. And you see that there are small galaxies where the emission comes out from the very central regions. And then there are big galaxies where the emission is more extended. And it turns out you can correlate this radius of these galaxies, which you have with rotation, and you see rotation depends very critically on this radius. These compact galaxies have small rotation. They also have small masses, because we still have a Tully-Fisher relation for these high redshift galaxies, so rotation depends on mass. And so in that sense, these are small mass galaxies and rotation is small, and these are high mass galaxies which are more extended and the rotation is high. That is not in itself something that is different to the present day universe. But something else is very, very interesting. When you look at the random motion of material in these galaxies, then if you go to the redshift 0 universe, the dispersion or turbulence of your disks is roughly at 10 kilometers a second. That's because we believe the ISM is a thermostat that burns, it runs at 10 kilometers a second. But when you go to the high redshift universe, you see that the velocity dispersion is much, much, much higher. That's the main difference between the high and the low redshift universe. The high redshift galaxies have much more random motion than the low redshift universe. In addition, you see that the rotation goes down when I go to galaxies that have less mass and that are more compact, but the dispersion is actually going up. Which means, if I put this kind of correlation into here, which is roughly flat, that if we go to the low mass galaxy, they become strongly dispersion dominated. And if I go to the high mass galaxies, they are still rotation dominated, but not so much. Dispersion is still something you cannot forget. So compared to the low redshift universe, where dispersion is so small compared to the rotation that you can always forget it, in the high redshift universe, the random motion of the gas and the stars, which results from probably something, actually I don't know, and I'm not sure I will ever get to this, is much, much higher. And this has a very, very important effect. And the effect is shown here. Well, this is the hydrostatic equation, which you all know. Centrifugal force V squared over R is balanced by gravity, the gravitational force of R. And usually this is what we use in order to infer the intrinsic mass distribution from the rotation curves. And then we find we see more mass than, we find more mass in this equation than we see, and so we infer some dark matter. But if you have a system where the pressure, and in our case it's turbulent pressure, kinetic pressure, is not negligible, you have to add this pressure term. The pressure gradient exerts a force. Pressure itself has no force. You know, you can have infinite pressure, and the pressure has no effect on you because it's constant. You know, who cares whether we are in a high pressure and low pressure environment? If the pressure is everywhere the same, it has no effect on us. The effect becomes interesting when you get into a pressure gradient. The pressure gradient exerts a force, and it's given like that. And you see immediately what happens. If the pressure gradient is negative, that means the pressure decreases when we go to larger radii, then this is actually negative, and that means it compensates for parts of the gravity. It means that the rotation velocity will decrease. Not because there is less gravity or there is no mass out there, but because you have a pressure gradient that decreases the effect of gravity. It's like what I call the negative dark matter. And so the question is, what happens if you take this pressure term into account, and can this explain these declining rotation curves? Now, if we sit in a certain turbulent medium with a velocity dispersion, then the pressure can be written as rho sigma square. The gravity is just the rotational velocity, if pressure would be negligible, square divided by r. So this is V0 is the term if pressure gradients are negligible. And then you can put this into there, and then you find your measured rotation velocity square is the gravity-driven rotation velocity square plus this term over here. Now, we add the observation that the velocity, that the surface density of our disks is exponential, and we need now to connect the surface density to the real density. The surface density is 2 times the scale height times the real density. The central density at redshift at z equals 0 in an isothermal disk, and the scale height of your disk you can show is sigma z square, the z velocity dispersion of the disk divided by pi g sigma. And you see already if sigma is an exponential decreasing function, then the scale height is increasing with radius if the sigma z is not changing, so the disks are flaring. And you see something else. If you now work out the density from this relation over here, then you see you have capital sigma divided by h, but h also depends on 1 over capital sigma. So you see the density goes proportional to the surface density to the square. That means if you have a certain decrease in surface density, it's kind of amplified in the central density. That means the pressure gradient inferred from the surface density can be amplified strongly when we go to density, simply because when you go farther out, your scale height increases, and then if you have a certain surface density, the central density becomes smaller because the scale height becomes higher. Yeah, so it becomes larger. So you get this kind of density distribution. It is a constant. These disks seem to be all isothermal, and goes as e to the minus 2r over rd. And if you now put this into this equation over here and solve for that, then you find something very interesting. You find that the rotation velocity which your disk has to have in order to compensate for the pressure effect and for gravity is the gravitational part, which would in general be a flat rotation curve, minus 2 sigma square r over rd, where r is the radius you're looking at and rd is the disk scale length. And you see when you go to the other parts, especially when sigma is large, this has a very strong effect on the rotation curve. And it's something which is very well known. It's called asymmetric drift. We see this also in the solar neighborhood, where the rotation of the stars is actually a little smaller than you would expect from gravity. It's very easily explainable. If you have stars on elliptical orbits, if you want the dispersion, you want to put the stars on elliptical orbits. Because if the stars on circular orbits, you have no random motion part. But if you put stars on elliptical orbits, you can only do this if you remove angular momentum. Otherwise, it would be circular. So that means the rotation you see is smaller than on a circular orbit. And that is basically the effect we see over there. And it's a very well-known effect in protoplanetary disk research, because in these kind of planet-forming disks, you have dust particles. These dust particles move, don't feel a pressure term, and just move on their ballistic orbits. But you also have the gas, and the gas feels the thermal pressure gradient, and therefore its rotation velocity is a little less. And that leads to the problem that the dust particles are actually moving through the gas with a net velocity, which slows them down. And there's the old problem that if you wait a little bit, then all your dust vanishes into the sun, and you can't form any planets. And the people try to solve it, and they solve it by adding some eddies all over the place in order to trap the dust or whatever. But it's a problem for protoplanetary disks, and it seems also to be a problem for high-redshift galactic disks, because there the velocity dispersion is not negligible. Okay, so now let's build a simple toy model of a high-redshift galaxy. We assume the galaxy to have a specific angular momentum given by the real parameters, and the lambda is 0.035. We assume the disk mass fraction be 0.035 and the mass fraction be 0.05 from observations. If we fix the dark matter halo with a certain real mass at redshift 2, we know the real radius, we know the specific angular momentum, we can build the exponential disk with its correct density distribution and correct scale height, scale length, and then we can simply add the gravitational force of the disk and see what kind of rotation curve we get if we also add this kind of NFW halo, which we assume to do this. And here's the result. If you take a galaxy, which is typically real mass of 10 to 12 solar mass, and you put in a disk with this kind of lambda parameter, then this is the Freeman disk rotation curve, which you get alone for the disk. This is the halo part of the rotation curve, which you get by just putting an NFW halo in. And if you add both up, you get this total rotation curve, and indeed it is flat, as you would expect. You get typically disk radii of 3 kiloparsec, rotation velocity of 220 kilometers per second. It's all in good agreement with the Milky-Way, so this model is working. And if we now go to redshift 2, then you see that the disk is a little more concentrated, because at redshift 2 I told you that all scales of a factor 2 smaller, so it is a little more peaky. The halo has this kind of profile. It's also more compressed. And what you get basically at the as a result is again the flat rotation curve, no signature of a decline, and the rotation velocity, which is a little large because everything is compressed. And if you now compare this to the observations, you already have a problem. The disk is too small, the rotation velocity is too large, and we do not see any signature of a decline. But this was a solution where I didn't put in the pressure correction and assumed sigma equals 0. If I now go and add the pressure term with a typical random motion of 60 kilometers a second, that means I add this term, then everything is completely changing. Remember, this was the sigma equals 0 rotation curve if pressure term is negligible. If I now add the pressure term, the disk radius becomes a little larger. It's not anymore 2 kiloparsec, it's 3 kiloparsec. Why is it larger? The rotation velocity is decreasing because of the pressure term. But the specific angular momentum is the same. And so if the rotation you now allow is smaller, the disk has to become larger to have the same specific angular momentum. You solve this problem that your disks were too compact. In addition, because you have this term, your rotation velocity goes down from 250, which is not really observed, to something like 210, which is in very good agreement with what we indeed see. So this all works very, very well. And you see, because this term becomes more and more important the farther out you go, you see that the rotation curve is actually reaching a peak and then is strongly declining. And if the velocity dispersion would be constant all the way to the edge of the disk, there's a region where the rotation velocity reaches 0. Which means you don't have a disk at that radius anymore. The scale height is exponentially increasing of your disk and it becomes a spheroid out there. Now how that looks geometrically like, I haven't yet been able to figure out, because if you have a disk in the inner region and want to form a spheroid, well, the sphere has to go somehow around. I mean, but then it's... So I haven't yet constructed a dynamical model where the disk has a finite radius, because we become completely dispersion dominated and the rotation becomes 0. It would be fun to work that out. And I am not sure whether this is dynamically stable and so on. It just simply follows from this very simple result. Well, it turns out if you would have a redshift 0 galaxy, the typical profile would look like that, and you would crank up the random motion to 60 kilometers a second, you get the same result. So it's nothing that is special to high redshift galaxies. Low redshift Milky-Way type galaxies would do it too. The only problem is we do not get these high dispersions for the low redshift galaxies for whatever reason. That's why we don't see it. But if you go to elliptical-like galaxies, where the dispersion is high, then indeed you see evidence that the rotation curve is going down in the outer part, which is precisely this pressure effect. So you now can put this into this correlation over here, and you basically see, indeed, if you take the standard rotation curves you would expect at 60 kilometers a second, you get this blue curve, and it fits the observations very well. So this kind of negative dark matter is just an evidence of the additional pressure term, which has usually been forgotten. So that seems to work out very nicely. Everything is in agreement. We do not have to worry about anything else. Mont is still correct, because the pressure term doesn't care about Mont or whatever. You know, it's a gravity part, so we can't really rule out Mont, unfortunately. Or it's still fun to have some people around defending Mont. It makes the life, you know, if you go out for a beer, you need to talk about something crazy. So why not Mont? And maybe it's right. You never know what happens. Anyway, so this is all fine. But there's a problem. And I still have, how much time do we still have? 10 minutes or so? 10 minutes. So let me tell.
It's recorded, so anything you say about it.
Oh, you tell me now? Too late. Okay, don't listen to what I'm saying here. That's okay. So, at the moment, what we did is we normalized this to 1. So all scales have been removed. But we can now look at the real rotation velocities and see is this in agreement with what we know from standard theory. And do we really have the mass available to add dark matter, or is there a problem? And just to show that this is a problem, here is what I want to do first. Well, you can work out the dark matter mass within the half mass radius of your disk. You just simply take the rotation velocity you measure. Now you add this correction term. That is the real gravity rotation curve now, which you have, divided by g times r1 half gives you the dynamical mass inside r1 half. You subtract half of the disk mass, because that's r1 half is chosen such that half of the disk mass is within that, and you subtract the bulge component. What is left behind is the dark matter part. And then you divide this dark matter mass by the total mass you have inside your half mass radius. That gives you the fraction of dark matter you have inside the half mass radius. And you then can plot this FDM versus something. Let's say the rotation velocity of your disk. And that is the result. Now, these are present-day galaxies. The Milky Way sits somewhere here, 50% of dark matter within the half-mass radius, which is of order 6 kiloparsecs and so on. And this is where the high-redshift galaxies sit. And you see they are uncomfortably low in dark matter fraction. In fact, if you put all the 200 galaxies together and make a stacked sample, the dark matter fraction is only of order 10%. Well, if you look at what you usually get if you do this simple cosmological model I just told you about, you get something like 30–40%. So quantitatively, I would expect much more dark matter within the half-mass radius, if we take standard cold dark matter NFW profile, than what is seen. And some of these things are really, really puzzling, because these galaxies have kind of no dark matter, no room for dark matter within the half-mass radius. Well, you can go a step further and say, okay, I don't talk about dark matter. I just look at the dynamical mass within my half-mass radius, which I get from my corrected rotation curve, and compared to the total mass I see within my half-mass radius. That doesn't mean anything with respect to NFW profile, it's just simply something like that. So you take V1/2 square, add your correction term, divided by G times R1/2, that's the total dynamical mass, taking away the pressure factor. And then you say the F bar is half the disk plus the bulge divided by the dynamical mass. The dynamical mass should at least be equal to all the baryons. You see, so F bar should be 1 or smaller. Now here's the sample of galaxies. This is the upper limit. This is what physics tells you. Nothing should exist up there. But you see roughly 50% of all these galaxies at high redshift lie above this line. And some really extreme. And well, okay, there is a dependence a little bit on the scale length of the disk. I don't know what it means. But this is too much. And this is, well, I wouldn't care about a factor 2 or 1.5, but this is going beyond a factor 2. So Newton's laws are not working for high redshift galaxies. And this pressure effect alone can't save this. Qualitatively, we get declining rotation curves. Quantitatively, looking at the numbers, we miss something. You know, there's not enough dynamical mass you just get from the, you need an even higher pressure term to do it. But there is no way. We know the velocity dispersion very well. And going to these extremes makes it too high. So at the moment, we are stuck with this kind of result. And I have no solution, and Avi is uncomfortably silent. Well, usually he comes up with a good explanation right away.
So here is another. So the mass to light ratio of the stars. Is it possible that the IMF is different than the local one, so that you overestimate the mass of stars?
Yeah, well, this is where.
Baryon,
Yeah. Well, you assume yes.
Or stellar.
No, this is basically the baryon fraction. The stars you can sometimes measure, and then the gas you measure basically from the emission. You have an H alpha profile, so you have to conversion factor in that. But I think that has been very carefully. Erica knows a lot about it. She is the observer in the group. So
it's harder. It's easy to hide mass, but it's harder.
It's harder to overproduce. Yeah. Well, okay, where F bar is too high, we need to bring this down. Yeah.
Given the luminosity, we need to have fewer, less
Yeah.
galaxies.
And then why should it depend on radius? I mean, yeah.
Are there assumptions about some sort of equilibrium going into these?
Yeah, of course. This is always some
So,
hydrostatic
I think in
equilibrium.
high-redshift galaxies, you might have situations where you're not in these equilibriums.
Sure.
And so
Yes.
the equations may not.
But that really doesn't make much of a difference. First of all, the galaxies look pretty normal in their rotation properties. So any equilibrium must be close to equilibrium. And the factor 1.3 or so doesn't make any difference. And you can show the equilibrium is reached very quickly again. And you really have to have the galaxies far out of equilibrium that you can't use it. And so at the moment, the equilibrium solution doesn't work either. So this is a problem we have. The other problem is to explain these high dispersions and how to interpret what this means with respect to galaxies. And I now have 12 minutes left. Should I open this Pandora box? Because of another, it's not a problem. Oh yeah, okay. Nobody's yet asleep. Okay, so let's go to this. So there are two ideas, and Blakely has been involved in that to a large extent. We have a strong debate, which is wonderful. I love debates, especially with a beer. And so the dispersion could have two sources. The most natural source for the high dispersion is that you have stellar feedback. You have large star formation rates, and these kind of push the gas around. That could lead to the dispersion. And the new theory, which is now favored by many people, and I have written papers about this too, but I don't believe in it anymore, but still write papers because you never know. You better have your kind of, how do you say, your money everywhere. I just lost a lot of money because I was doing this damn Bitcoin thing, and I you know, this is really dangerous. You never ever, because I just in this year, January, I thought, wow, it's cranking up. Put my money in, exactly the same day it came down, as if it knew. I don't know how they knew that I put my money in. Didn't put it much, $100 or so, but it's still, it's amazing. So you better have both. And I can't go into these details. Blakely has probably told you already. These are the observations. These are their models. Stellar feedback doesn't produce enough energy input, whereas the gravitational disk instability does. So let me quickly explain what the disk instability is. So the idea is the following. If you have a disk which feels self-gravity, if the disk has not enough pressure, enough random motion, self-gravity will lead to structure. The disk will have regions collapsing onto themselves, and it will produce substructure. The substructure requires motion that is not circular, because in the circular motion you don't get substructure, you generate dispersion. So that is the instability, and so you can write this down as the so-called tuber parameter Q, which has the pressure effect, which is stabilizing, and the destabilizing gravity effect, and you can basically demonstrate when Q is larger than 0, the pressure is dominant, the disk is not unstable, and when Q is smaller than 0, the disk is highly unstable, and you get these kind of instabilities, and you might actually crank up the velocity dispersion by that. Then you can put in some simple equations, V rho squares GM over R, surface density Z, and then it turns out that Q can be reduced to this kind of simple formula. It's proportional to the velocity dispersion you have. This is the gas fraction you have in your disk, and this is the rotation. Now, the idea has been, and we all use it, but I'm not sure it's right, that Q will always regulate itself to or something of order 1. Why? Well, if Q is larger than 1, the velocity dispersion or pressure is so high that everything stabilizes, and then you can't drive random motion anymore because this disk is stable. Whatever random motion you have dissipates, and so the sigma goes down and Q goes down. And when Q is too small, the gravity becomes so dominant that you drive lots of random motion, sigma goes up again, so you will always get close to marginal stability, and so Q should become of order 1. But this only works if sigma is a stabilizing effect. And I want to tell you this is not at all true. Sigma is actually most destabilizing. And that's the reason. Well, if you believe that, then you can work out from the simple equation we had that sigma must be proportional to the gas fraction. And indeed, that explains if you go to high-redshift galaxies, the gas fraction is high, that's why sigma is high. And in the low redshift universe, the gas fraction is small, that's why sigma is small. So you can do this, and it basically works. And here's a numerical simulation that basically shows this. My graduate student Baryons has been doing it, and it's really, really nice. You already see that it's not exactly what you believe, because the tuning instability is a ring instability. It doesn't form clumplets, it forms rings. But you see that these rings immediately break up because of small asymmetries, and then they form clumps. And if you measure the random motion in these clumps, did you see how the velocity dispersion is going up? And the Q, if it was small, is increasing with time. So that works very nicely. Now you can argue, well, okay, these clumps, because we wanted to reproduce a high-redshift universe and these high-redshift galaxies, there are only 5 massive clumps seen, and these are billions of clumps. That is not, that's not in agreement, but you know, a good graduate student always finds an answer. And so Manuel found an answer. And that is clever. He said this is an observational problem. They can't resolve these clumps because they are too small and the beam size is too big. Then I say, okay, but if they are all over the place, you would still see something smooth. Then Manuel said, no, if you look very carefully, you see that these clumps cluster. They form what he called clump clusters. And actually you can show that you have these rings and they break up in these clumps. These clumps begin to interact with each other. And then you see this grouping into the clump clusters. So that works very nicely. Well, it's now rotating in the opposite direction. How did he do that? The clock is, it's funny. I never saw this. Anyway, you see, I don't have the time. You see that there are the clump clusters forming. The clumps are organizing into clusters, and then Manuel did the most wonderful thing. This is his galaxy, a little bit tilted because observations are also slightly tilted. And then this is highest, you have the full width half maximum is 0, you have perfect resolution. And now if you smear this out, basically to a resolution which you see, then you see all these details merge, and what is left behind are these clump clusters. And if you smooth it out to about 1.6 kiloparsec, this looks like a ring of 5 massive clumps. It's not the case. These are substructures, but you don't see it. And this is in perfect agreement with what you see up there. And he said, okay, if an observer would ever have the resolution, then this is what you would look like, but we don't have it. So disk instability seems to work and seems to explain these kind of higher redshift galaxies. So that's what we assume. But what is the energetic drive of this? We said it's gravity. But gravity is not a pressure. If you have a cloud collapsing, you generate, from the outside it looks like converging flow, and you get a broad line, because something comes towards you and something moves away from you. But this dispersion which you measure, this non-circular motion, is not pressure. It's not random motion. It's coordinated collapse. This does not contribute any pressure. It just does the opposite. It tells you that the whole thing is highly gravitationally unstable and collapsing. So a disk that is unstable and forms all of these clumps is not producing random motion. It produces collapse. And that's just the opposite of what you need to pressurize your disk. Just the opposite. And basically, okay, no, that I don't want to do because it goes a little bit too far. And I would like to show this over here because we are getting to the end. This is a simple calculation where we took a very, very cold disk. The disk was gravitationally unstable. It was forming these little clumplets. The clumplets were growing in mass, becoming bigger and bigger. And here you see a higher resolution of that. We looked at the Q parameter. It's really cranking up, becomes of the order 1 and 2, as you would expect. And then we looked at the potential of this kind of environment. The idea is that you have this random motion in these disks. The random motion is generated by the gravitational instability, but you need to drive this somehow. And so the idea was that this random motion is interacting with each other, and the whole disk, because of this dissipative random motion, is shrinking in size. The potential energy which you get by the shrinkage of the disk is what drives the random motion over a very long time. And so we did this over here. We looked at the potential, and this here, the red part, is the initial potential well. And then we looked at the time when the disk has become highly unstable. And what you see is that the potential well is much deeper. And this kind of energy difference between the initial potential and the potential of that is what can drive this random motion. Yeah? But it turns out that this is not leading to any shrinkage of the disk. If you average the distribution of particles such that you keep the radius of each particle, but you give it a random phase, the disk is smooth again. And if you then measure the potential well, it's this kind of black curve. And you see the disk is not shrinking, transferring potential energy into kinetic energy. The random motion which you generate is a local effect. It comes from the fact that you have gravitationally dominating clumps, they attract the surrounding. And if you then look at this in projection, you see lots of collapsing cloudlets. And that is what you infer the velocity dispersion. And the potential energy which is released is just simply because you make these clumplets denser and denser and denser. Now, this is a problem, because if you let the things collapse and collapse and collapse, they will become a black hole. And in a short period of time, all your disk has disappeared into black holes. So to keep this process running, you need to disrupt the clumps again, to put the energy back in, which you got released by this collapse, which you call is your velocity dispersion. Now, what kind of process can disrupt the clumps? The only process I know is stellar feedback. So I argue that at the end, it's again the stellar feedback which drives the turbulence in the disk. Because otherwise it would kind of be a one-way street. Yeah? And so, whether Blakeslee likes it or not, I still argue that in order to keep this random motion going, we need a stellar feedback. And I also argue, that this Q is kind of very misleading. What we measure is a high sigma, but the high sigma is caused by gravitational collapse, and it is not a pressure. As I said, it's just simply the opposite. It's gravitational collapse. It doesn't contribute to the pressure itself. And so I wonder then, why should Q at all go to 1 or 2? What is the self-regulated mechanism that leads to this kind of thing? It's not the typical Q. Tumor instabilities, may be something else, and I don't know what it is. And we are still working on this. Why do disks behave like Q1? And we also work on the stellar feedback process. Can we generate enough feedback in order to break these clumps apart as quickly as they form in order to get this dispersion right? So there are these open ends. We still don't know where the dark matter is in the inner regions of these galaxies. And we still haven't figured out how we can drive this high turbulence, which is required basically to get this pressure effect. As I told you, gravitational instability is not a pressure effect. And indeed, when I did these unstable disks, I got a lot of sigma, but I never saw a declining rotation curve. Well, if I would have used my formula, there would have been a strong decline, but there wasn't a decline, simply because this inflow doesn't produce a pressure. So I think we are still a little bit stuck, and this is just early days. And thank you for listening.
Time for a couple quick questions. Please.
So first, Andy, I would say it's both and.
Oh, yeah, you're already
Yeah, you
coming
have-
in. Yeah.
Well, we have a new paper actually.
That's much
with
better
feedback
than a week ago.
plus-
Okay.
No, there's a new paper. John's
Yes,
also on the
yes.
paper where we combine the tumor instability for the gravitational driving of sigma
Yes,
plus feedback.
yes.
And actually, interestingly, there's a redshift dependence on which dominates the contribution to sigma. I wanted to ask in the nice tumor instability simulations you were showing, what else is in there? Is it stellar feedback?
Yes, we
There?
had this without and with stellar feedback, and the results do not change.
Okay.
The
So you
feedback.
don't get full collapse when you don't have feedback.
Yeah, then
So
if I
what's
put
causing the pressure
well,
support?
what happens is if I have feedback, then I don't get the code does not crash. In this case, without feedback, everything collapses and then the code crashes because it goes to infinite densities. Or you form this way a mini disk where everything is rotating very fast. With feedback, you destroy the clumps again and you rebuild them. But you need an enormous amount of feedback to really do this, especially because you are so gas rich. And so we have to crank up the efficiency of feedback enormously. Which I agree is a problem because I do not really know how to generate that amount of energy. Especially in these very dense clumps. You know, these are the clump clusters, but still the densities are very high. And maybe the IMS is different. Maybe that's part of the solution.
Yeah. And I wanted to ask, because it seems like the running thread, the theme of your talk
Yeah.
is the mass accretion. Right? The
Yes.
mass accretion sets the star formation rate.
Yes.
And potentially, although it's still debated, the mass accretion rate
Yes.
sets also the sigma and
Yeah.
potentially
Yeah.
can explain
But I love
these
this.
profiles.
I like this. Yes, it's indeed true. I wrote a paper with Bruce Almgren a long time ago where we argued that we have enough energy in the accretion process to drive the turbulence you see. That was forgotten because everybody got into this instability, turbulence driving. But I think it works. So mainly you have to
even with the
illuminate.
disk instability, the mass accretion, you have to have the mass accretion, otherwise your,
well, the mass
your
accretion, exactly.
big sigma goes down.
Yeah, the mass accretion is actually even nicer. The mass accretion initially is so strong that this doesn't become unstable. So you can build a gas-rich disk, which is always a problem. If the disk immediately forms stars, you never form the gas-rich disk. Yeah. So, and then after some time, the surface tension is high enough that the disk also becomes marginally unstable, and then it's wonderfully working. So
That's the thing that connects all of it.
yes, that is right. That is not bad. But
Yeah, I just want to get my head around the physical picture of these galaxies. So you measure the dispersion from H alpha, from ionized gas, is that correct?
yes, but not in all galaxies. We also have molecular gas. In some cases, we find similar random motion.
That's probably from the line width,
Yes,
the average
exactly.
line width. of the
Exactly.
galaxy.
And you, of course, you need to correct for the shear. You know, the shear, a shear disk
Correct.
generates some dispersion, which is not real dispersion. You need to correct for that, yes.
And then I would imagine for your model to work, that dispersion that you're measuring from the gas must also be the dispersion that characterizes the stars.
Yes,
So the stars have all this very high dispersion. So
they have
That's
to
why-
have, yes,
yeah.
initially the same, but later on the dispersion of stars becomes even larger because of scattering.
right. So my question is, how long does it take once the gas is gone, mostly, to dissipate that turbulence and get to a situation so the galaxy looks like Galaxies as equals to?
Today.
I mean, what's the mechanism?
Well, if the gas is gone, you can't dissipate any dispersion, so the gas must still be there. But suppose you shut off feedback, and you want to calculate how.
No, but you have, now that I'm talking about the stars. How,
The stars, no, that's the problem. The stars will never lose the random energy. They will keep it. So these stars form with velocity dispersion of 60 to 80 kilometers a second. They can never form a thin stellar disk anymore.
so how do they get to the thin states?
They must either be thick disks or they are spheroids. So these galaxies have already so much, they have about 5 to the 10 solar mass of stars with a dispersion of 60. There's no star forming galaxies of redshift 0 that has this. So these galaxies will never form low redshift disk galaxies. They might form ellipticals or whatever, fast rotating ellipticals or something like that. Yes.
Okay, last question.
Okay, so say I make the measurement of the disks and they're not flaring.
Yeah,
Right.
well, yes.
So does that mean there's negative?
Hey, I need to take this now. You're right. There is this problem that if the velocity dispersion is constant and the scalar height goes proportional to the velocity dispersion square divided by surface density, if the surface density is exponentially declining, the scalar height must be exponentially increasing. And that's not the case. So the velocity dispersion is maybe declining outwards. Yeah.
But then do you not have as much asymmetric drift? Like, can you not?
Now then that would make, again, the problem severe in explaining the decline in the rotation curves. Now you can solve that or argue that the scalar is given by sigma z, the z component of the dispersion, but the pressure gradient in the disk is given by sigma r, as sigma x squared plus sigma y squared. And the velocity dispersion can be asymmetric, it can be non-isotropic. So sigma z is adjusted so that the scalar becomes constant, and sigma xy is different. Yeah? That is the way out. It, of course, now leads to an anisotropy parameter, which one has to take into account, which is an additional free parameter, but I think that would be the way out.
And a quick follow-up. Would
Sure.
this help also in revisiting the fractions of the dark matter?
No, that would make it worse. Look, the reason why this pressure effect is so important is the fact that the density goes down as the surface density square, because the scalar height is increasing. So you get this 2 sigma squared times r over a disk. This 2 is important. Without this 2, you wouldn't have a strong effect. But this 2 comes because the disk is flaring, and so the density in the disk plane goes down quickly. If you don't allow it to flare, this 2 goes away. And then the pressure effects are too smaller, and then we don't get enough pressure effect. So actually the flaring is required to get a strong gradient in pressure, as much as we need to explain these curves. And if you get rid of that, you make the problem again worse. But okay, maybe it's the way it is, and we have to come up with other solutions. Right? So just, yeah.
All right, well, let's thank Andy.
So how well established is it that they're actually